MS Ramaiah University of Applied Sciences.
Hi students, let us have discussion on calibration of flow meters. Measurement of flow rate is one of the basic measurements in engineering. In the process industries, flow measurement is colloquially called as flow rate, discharge or metering. Some of the flow measurement examples include water flow rate measurement using turbine flow meter in domestic water supply line, milk flow rate measurement in the packaging of milk, flow rate measurement of other common fluids like oil, juice, chemical flow rate measurement in chemical plants, air and steam flow measurements. A flow meter is a device to measure the flow rate of internal flow. A variety of flow meters are available for the purpose, such as venturi meter, orifice meter, flow nozzle, elbow flow meter, cone type flow meter, rotometer, ultrasonic flow meter, turbine flow meter. The type of flow meter selected is based on the application, type of fluid, nature of fluid flow. Periodically, these flow meters are calibrated to make sure there are no errors due to repeated usage. The calibration is a process of finding a relation between the measured value from a device to a standard value or standard reading from known device. First, we are going to concentrate our efforts and learn some commonly used flow meters available at Ramaiah University of Applied Sciences Fluid Mechanics Laboratory. Later, we are going to understand the calibration procedure. Venturi meter, orifice meter, flow nozzle, rotometer, turbine flow meter. A venturi meter is commonly used to measure flow rate of gas and liquid flow. It can be easily scaled and the loss associated with it is small. It is used in power plants and civic water supply. Its construction includes an inlet, throat, and an exit. The pressure difference between inlet and the throat is measured. Flow rate is calculated based on Bernoulli's principle. Several fluid assumptions such as inviscid, that is zero viscosity, irrotational, incompressible flow are made about the under consideration. The flow rate is given by Q is equal to CD into square root of 2GH into A1 A2 divided by square root of A1 square minus A2 square, where Q is the discharge in cubic meters per second, CD is the coefficient of discharge, A1 is the cross-sectional area at the inlet, A2 is the cross-sectional area at the throat, H is the manometric height difference between inlet and the throat. The orifice meter. Orifice meter is one of the most compact and simple flow meters routinely used in fluid packaging industry. The construction consists of a plate with the orifice either at the center or in an eccentric position. The fluid losses in orifice meter is higher compared to the venturi meter. This type of flow meter is generally used in situations where fluid losses can be neglected. The pressure drop between the inlet and vena contracta of the flow is measured. This data is used to find the flow rate of fluid. Flow nozzle. A nozzle flow meter is similar to orifice meter, with the exception that the plate consists of a nozzle instead of an orifice. The pressure difference between the inlet of nozzle and the nozzle outlet is measured. The cross-sectional area of the nozzle at the points of pressure measurement are known. With these data, we can calculate the flow rate of fluid. Turbine flow meter. Turbine flow meter is commonly seen in the domestic water supply line. It is more accurate at the flow rates associated with the civic water supply. It contains a small turbine that rotates when there is a flow. The rotations of the turbine are converted into flow rate measurement. Rotameter. Rotameter is a flow meter that has a very distinct appearance. It has a conical outer tube that has marking for the flow rate. And within this conical tube is an internal float. The float rises as the flow rate increases. The rise of the float can be used to measure the fluid flow rate. This flow meter has a limited range and is applicable in the case of transparent or translucent fluids. Typically used in liquids, but some flow meters designed for LPG and other organic gases are available. It has to be always installed vertically. Fd is the drag force, Fb is the buoyancy force, W is the weight of the float. The position of the float is decided by the force balance of the float. Weight of the float is balanced by the buoyancy and drag forces. As mentioned above, the reading from a rotameter is directly taken from the top of the float position. The calibration of all the flow meters are conducted by setting the rotameter as the standard. However, any other calibrated standard can be used instead of rotameter. Error between the measured value and the standard value are measured and plotted to get the calibration curve. Setup consists of all 5 flow meters connected to a storage tank via pump. The pump output is measured using rotameter.
Hello everyone. Today we shall be conducting an experiment on various flow meters. In our fluid mechanics laboratory, we are having venturi meter, orifice meter, nozzle meter or the flow nozzle, and a rotameter. The setup consists of a collection tank where the water is being stored. From the collection tank, it is connected to a centrifugal pump to pump the water through the circuit. At the downstream of the pump, we have a discharge valve to control the flow rate of the water through the circuit. From the discharge valve, it is connected to a rotameter which indicates the flow rate through the circuit. From the rotameter, it is further connected to different pipelines consisting of different flow meters. From the rotameter, it is connected to a header consisting of 4 different pipes. On each of the pipes, we have an individual flow meter installed. The first pipe, we have a venturi meter. On the second one, we have an orifice meter. On the third, we have a nozzle meter or the flow nozzle. And on the fourth, we have a turbine flow meter which is being used by city corporations to meter and check the flow rate of individual houses. On each of the pipelines, we have an individual isolation valves which can be either opened or closed in order to allow the flow only in that individual pipes. Further downstream of the flow meters, it is connected to a collecting tank where the water can be collected and measured. This measurement is done using a piezometer, using which we can calculate the actual discharge of the flow through the pipe. To calculate the discharge through the rotameter, we already have graduations that are inscribed on the rotameter in liters per minute. To calculate the discharge through the venturi, the orifice and the nozzle meters, we use a manometer using which we calculate the pressure drop, and using the value of the pressure drop we can calculate the discharge through the individual flow meters. To calculate the discharge through the venturi meter, it is required to measure the pressure at the inlet of the venturi and at the throat of the venturi meter. To measure the pressures, there are tappings at the inlet and at the throat which are connected to a manometer, where we get the difference in the height of the mercury column, which can be used to measure the pressure difference between the inlet and the throat of the venturi meter. In the orifice meter, we have an orifice which is present at the center, and to calculate the discharge through the orifice meter, we need to measure the pressure at the inlet of the orifice and at a point where the vena contracta for the orifice is present. From the 2 points where the pressure has to be measured on the orifice meter, it is connected to the manometer, where we can measure the height of the mercury column, which gives the indication of the difference in pressures of the orifice meter. In the nozzle meter, the nozzle is present at the center, and to calculate the discharge, we need to measure the pressure at the inlet of the nozzle and at the outlet of the nozzle. To measure the pressure between the inlet and the outlet of the nozzle, there are tappings which are connected to the manometer, where we get the readings in terms of height of mercury column, which gives an indication of the pressure difference between the inlet and the outlet of the nozzle meter. Now let us go ahead and start with the experiment. Before starting the experiment, we shall first ensure that the discharge valve of the pump is completely open, and at the main header we should ensure that at least one of the valves is completely open, and then we switch on the main supply. As we switch on the main supply, we should get an indication on the panel which has a red bulb glowing on. In the beginning, we shall calibrate the rotameter against the venturi meter, because venturi meter has a coefficient of discharge close to 0.98 to 0.99. So keeping the reading on the venturi meter as a standard, we shall calibrate the flow of the rotameter. Now I have kept the main valve of the venturi meter open near the header. Now let us switch on the pump and start with the experiment. First, we shall set the reading on the rotameter to 40 liters per minute by slightly closing the discharge valve. Now the water is being flowing in the venturi meter pipeline. To calculate the discharge across the venturi, we shall open the tapping of the inlet and at the throat of the venturi. We should ensure that the ball valves on all the other flow meters are maintained closed. After opening the ball valves on the venturi meter, we shall ensure that there is no air bubbles through the pipelines. We shall wait for a minute or so and then close the valves on top of the manometer limbs, and then the reading on the mercury column can be taken. The same procedure is repeated for different value of the flow rates. Now let us reduce the flow on the rotameter further by closely the discharge valve. At this flow rate on the rotameter, we shall calculate the discharge through the venturometer again using the manometer. By taking 4 to 5 different flow rates from the rotameter and the corresponding discharge values on the venturometer, we can stop the pump. There shall be some errors in the flow rates between the rotameter reading and the venturometer reading. We shall calculate the errors of each individual flow rates, and then we can calculate the correction that is required for the rotameter to be calibrated according to the venturometer flow rates. We must know that the orifice meter and the nozzle meter are connected through the rotameter and not the venturometer. Hence, in the first stage, we calibrated the rotameter against the venturometer. Now, for the calibration of orifice and the nozzle meters, we shall use the calibrated readings of the rotameter as the standard, and accordingly we shall calibrate the orifice and the nozzle meters. To calibrate the orifice meter, we shall first open the valve at the main header corresponding to the orifice meter and close the valve corresponding to the venturometer. Before starting the pump, we shall ensure that the discharge valve is again completely open, and then we shall start the pump. To measure the discharge through the orifice meter, we shall open the tappings at the inlet of the orifice and the other tapping which is connected to the vena contracta of the orifice. We shall ensure that the tappings of all the other flow meters are maintained closed. From the orifice meter, the tappings are connected to the manometer. We shall wait for a minute before all the air bubbles are expelled through the pipeline, and then later we shall close the manometer valves on the top of the limbs to take the measurement on the mercury column. We can measure the height difference of the mercury, which gives the corresponding pressure drop across the orifice. Now, let us further reduce the flow rate by slightly closing the discharge valve. The corresponding reading on the orifice meter can be measured by taking the values on the manometer of the mercury column. The same procedure is repeated for 4 to 5 different flow rate readings, and then after taking down the values on the rotameter and the orifice meter, let us stop the pump. After taking all the readings, there shall be some errors between the rotameter values and the orifice meter values. Remember, we need to take the calibrated rotameter values and not the actual rotameter values, because the calibrated rotameter is acting as the standard for calibration of the orifice meter. Now, after taking all the readings, we can measure the errors between all the different readings and then calculate the correction factor that has to be adopted for the orifice meter in order to calibrate that. Further, let us go ahead and do the same procedure for the nozzle meter. To allow the water to flow through the nozzle meter, we shall open the main valve at the header corresponding to the nozzle meter and close the valve corresponding to the orifice meter. Before starting with the experiment, we shall ensure again that the discharge valve of the pump is completely open. Remember, now we are doing the calibration experiment on the nozzle meter. Here we are again taking the calibrated rotameter as the standard because the nozzle meter is connected through the rotameter. Now we shall start the pump. In the beginning, we shall again set the value of the rotameter to 40 liters per minute by slightly closing the discharge valve. The corresponding reading on the nozzle meter shall be taken. To measure the discharge across the nozzle meter, we shall open the ball valves at the inlet and at the outlet of the nozzle meter. We need to ensure that the tappings of the ball valves connecting the manometer of all the other flow meters are maintained closed, and from the nozzle meter which is connected to the manometer, we need to wait for a minute before all the air bubbles are expelled out. After that, we shall close the valves on top of the manometer limbs and then take the reading on the manometer, which gives in terms of mercury column height. For the second trial, we shall close the discharge valve further by reducing the flow rate. The corresponding value of the nozzle meter is taken using the mercury height on the manometer. The same procedure is repeated for 4 to 5 different flow rates, and the values on the rotameter and on the nozzle meter are noted down. We shall observe that there will be some error between the flow rate readings on the rotameter and the nozzle meter. We shall calculate the errors and then finally calculate the correction factor which has to be adopted to the nozzle meter, which can be calibrated against the rotameter. We must ensure that the values on the rotameter has to be taken as the calibrated value of the rotameter which was done against the venturi meter. Once all the readings are taken, we shall stop the pump, and that concludes the experiment.
At MSR UAS, we spark your imagination unlike any other.